Let's work through two examples together. We're going to use the Newton quotient, which is this part of the equation right here. And we're going to take the limit of it as h approaches 0. This is going to give us the instantaneous rate of change of the function f at f of a, at fa. The function we're working with is defined right here. We've got x squared minus 4. Now we've got f here, and an f here, and an f here. And wherever we see this f function, we're going to put in this f function, except that we're going to replace x with a plus h. So let's go, and here for this function, we're going to replace every x with an a. So let's go ahead and do that. We've got f prime a is going to be equal to a plus h squared minus 4. That's this part of the expression right here. Now let's do this part here. We're going to have minus, I'll use the answer. Remember, replacing each x with an a squared minus 4. And the whole thing is going to be divided by h. And I want to make sure I rewrite my limit operator because we haven't taken the limit of the expression yet. Now, if I just sub in h equals 0, we're going to get something divided by 0, which we don't want. So we can't just go ahead and try and evaluate the limit right away. We need to simplify. We're going to do some simplification, try and reorder the numerator in such a way that we can remove this h down here in the denominator. So let's go ahead and expand the numerator. We're going to have the limit as h approaches 0 of a squared plus 2ah plus h squared. Notice we have a minus 4 here and a minus 4, so those are going to cancel each other out. So we're going to have a minus 4 plus 4, and we've got a minus a squared. And so this whole thing is going to be divided by h, our change in x, and we can simplify. The a squared is going to disappear, and these two 4s are going to sum to 0. Now, maybe just for simplicity, make sure it's clear for you following along, I'll rewrite what's left of the expression. We have the limit as h approaches 0 of 2ah plus h squared divided by h. And we can remove, or I guess we're going to divide h by h. There's an h in each of the terms in the numerator. There's an h in the denominator, so we can simplify, and we're going to be left with the limit of h approaches 0 to a plus h. And when we take the limit of this thing, we're going to be left with 2a. Or I could rewrite this as f prime of x is just going to be equal to 2x. If I replace my a with an x placeholder. So there's our answer. The instantaneous rate of change of this expression evaluated at some point a is going to be equal to 2 times a, or f prime of x is going to be equal to 2x. Let's take a look at another example. We've got the same instructions as last time. This time the expression we're going to look at is f of x is equal to negative 1/2 x squared plus 8x. Let's start off with our expression. We've got f prime of a is going to be equal to the limit as h approaches 0 of negative 1/2 times x plus h squared, right? This part right here. In fact, maybe I'll replace the x with an a, plus 8a plus h minus, and I like to put it all in a bracket so I don't make a sign error, a squared minus 8a. And I'm going to divide the whole expression by h. Now I'm going to go ahead and rewrite this and start simplifying. I've got f prime a equals the limit as h approaches 0. And we've got negative 1/2 times a squared plus 2ah plus h squared. And then we get plus 8a plus 8h minus 1/2 a squared, or I should say that's a plus 1/2 a squared minus 8a. The whole thing is going to be divided by h. Now looking at the numerator, we can do a little simplifying. We've got an 8a and an 8a here and here. And I can see that this a squared and this a squared over here, they're going to cancel each other out. So now let me rewrite this. I've got f prime of a is equal to the limit as h approaches 0. We've got negative 1/2 times 2ah. That's just going to be negative ah plus, oops, no, it's not going to be plus. We've got negative 1/2 times h squared. That's going to be negative 1/2 h squared plus 8h divided by h. 1, 2, 3, 1, 2, 3. So we had 3 terms in the previous line in the numerator, 3 terms in the numerator on the next line. So unlikely to have made a mistake. Now what about this h in the denominator? We can cancel out some of the h's, or really it's h divided by h equals 1. Then I can rewrite this as f prime a is equal to the limit as h approaches 0. I've got negative a, negative 1/2 h plus 8, and that's going to just be equal to negative a plus 8. There we've got f prime of a, and more generally we've got f prime of x, the derivative of f, which is equal to f prime x, or is defined as f prime x, is equal to 8 minus x. Just put the 8 first because it's kind of always look neater when a positive number is first followed by a negative number. And that's how we use the Newton quotient, or sometimes called the differential quotient, to find the instantaneous rate of change, also known as the derivative. So if the change in x is infinitesimally small, this is going to be your change in y.